Hi everyone, it's Mrs. Bustamante. In this video, we're going to talk about 8.3, which is population ecology, describing factors that influence population growth and dynamics and kind of how do we measure them based on population size. Is a population growing or shrinking? And then are we seeing exponential growth or not? We're also in this video going to talk about 8.4, which is the effect of density on populations, right? What does having limited resources do to the size of a population and how many individuals can be there? And then how do individuals respond to that, and what do we see as population size changes based on those limited resources? So before we get too much into this, I want to talk about what is a population, right? Well, we can go like big kind of to small, a biosphere, an ecosystem, a community, all the interactions of different populations within an ecosystem as a community. So what's a population? A population is really a group of individual organisms that interact with one another and with their environment in a complex way. Another way to think about it is that a population of something normally interbreeds with each other, right? It's typically in a given space. They typically have access to each other, and they kind of interact with those individuals versus populations or groups of individuals that might even be like them, but are in a different location, if you will. A population has properties that are different from those of individuals, right? So within that population, you can have differences in individuals, but as a result, they oftentimes cooperate with each other, but they also have competition between each other in that group of population as well. So having genetic diversity in a population is a good thing, right? This allows individuals in a population to respond differently to the same changes in the environmental conditions, right? What does that mean? Maybe not all individuals get affected by a disease and say die off, right? We've talked a lot about bacterial and bacterial resistance and that variety being good if you're a bacteria, right? If you're not a bacteria and you want the bacteria gone, not so good, but right, this idea of diversity makes it more possible for a population to continue on and reproduce. Populations that have little genetic diversity are at risk of what we say extinction, right? Things like condors, ferrets, prairie chickens, are really limited in their genetic diversity because their populations got so small that they're at risk for going extinct because they don't have a lot of variety in case something happens to them. Basically, a lot of different ways to respond to it. So now let's talk about population growth. Okay, there are several factors that influence population growth, and I'm sure you can actually think about a lot of them, but some of them we don't always think about. The age of reproductive maturity, right? How long does it take an individual to reach a point where they're able to reproduce? The number of offspring that they have at a given time can influence the population and its growth or not growth, I guess you could say decrease. The frequency of reproduction, how often does that reproduction happen? And then the survivorship of the offspring that are able to reach reproductive maturity, right? And actually being able to reach that reproductive maturity is important so they can continue to reproduce, right? If you just have a lot of offspring, but they never make it so they can reproduce, that can really influence the growth of a population too in the long term. So we can actually measure population growth, right? When we think about things that influence it, right, we can talk about increase due to birth, right, fertility. We can think about decrease as anything that causes something to leave a population, so a death rate, okay? We can also talk about immigration, things coming in, and emigration, I like to say, because it helps me think of exit, things leaving a population, right? So if we have more births or immigration than we do deaths or emigration, the population size will increase. Basically, if we have more individuals coming into the population than leaving, we see population increase. If we have more deaths and emigration, then we'll see our population decrease, right? Because it's going to have things going away and not enough to replace them. Okay, so we can use this to talk about our population growth rate. And our growth rate is going to be the birth rate minus the death rate, assuming that we have no migration, right? Because that will change what happens a little bit. So we can use this equation here. N is the population size, B is the birth rate, D is the death rate, and dt represents the change in time, right? So when we take all those things into account, we can kind of come up with a number about how fast a population is growing. I also want to talk about exponential growth, okay? Exponential growth looks like this. It's where you see the population grow kind of slowly at first and then radically increase. This would be an instance where birth rate exceeds death rate, and reproduction happens without any sort of constraints. Basically, there's no limiting resources, or reasons that the population stops growing. Now, this is an ideal model, and so it is actually not very realistic. There is no instance that I can think of where a population can just grow exponentially forever and ever and ever. Eventually, they will run out of some sort of resource that will limit them. But we can represent this with an equation. We say dn is the change in population size, dt is the change in time, n is the population size, and we have something called Rmax. Rmax is the maximum per capita growth rate of a population, okay? So it would be the growth rate that they would give us, and this would give us our exponential curve. You could also solve for any of these variables in here as long as they give you the rest of the information. Because, however, exponential growth is really not very realistic, we oftentimes use something called logistic growth to model population size. And it's where the birth rate and the death rate eventually kind of equal out, right? And so you see more stability in a population. It's where the density of individuals reaches or exceeds resources available. And so we see that typically sometimes we'll see it as an S curve, right? We see this exponential growth for a while, but eventually the population size starts to kind of even out. And that happens because of limiting factors or limiting resources that are available. And so the population can't continue to grow. Maybe you run out of space or food, for example. And we call this kind of maximum population size that can be reached in an environment, we call it your carrying capacity. We're going to represent it with K. It's where you notice that the line of your population size here, right, sort of starts to even out. And this is a much more realistic model of population growth. And you'll notice these dots, sometimes you can go over the carrying capacity or under it based on resource availability and fluctuations, and that's totally normal. But this is a much more realistic way of measuring population growth. It's much more what actually happens. What's our equation for logistical growth, right? dn is the change in the population size, dt is the change in time, R max is the maximum per capita growth rate of a population, n is population size, and k is actually carrying capacity. And here is how we put that into an equation, and again, we could use any of those variables and solve for any part of logistic growth. Now I want to talk a little bit about population density. And I want to talk about population density because it can influence the size of our population a lot, right? So when we think about density, it's really just the amount of things, if you will, in a given space. The more things you have in the same amount of space, we say the more dense something is. So population density is really just the number of individuals per unit area. More individuals in the same area or space, we say it's more dense. So you'll notice here we have a map of Oregon and a map of Washington. And if we look at areas in both places where there are cities, right, or big cities, we see they're more red and yellow, right, which means that there's more people there. There's more people in less space. And when we look at rural Oregon and Washington, right, we notice that there's much less people in that given space as shown by the colors there. We can also talk about the population distribution in certain areas, right? And we can describe it in 3 patterns. We can say that there's no pattern, they're just kind of random or spread out. Forests tend to be a lot like this. No pattern to the growth. We can have uniform growth. This often happens in plantations or territorial animals have a set pattern that they kind of will spread out evenly, right, in order to ensure the best growth, but notice this is typically things that we plant on our own for a specific reason. Or we can see clumped distribution or things in groups. Schooling fish are an example of this. Herding animals, flocking birds are all ways that we see this type of population distribution. So what are some factors that influence population size? We're going to talk about two kinds. We're going to talk about density-dependent factors and density-independent factors. So density-dependent factors, the size of the population will influence the individual's probability of survival, right? What does this mean? Okay, basically it just means that as density grows, and gets bigger, it's less likely for all the individuals to survive. And things that depend on the density, right, are things like food, water, habitat, other limiting resources. Sometimes this can be disease, predation, waste, and competition for resources. Basically, these are all things that depend on how many individuals are in a given space, right? That will influence population size, so that's why we say it's density dependent. We also have density independent factors, and these affect the size of a population, but they have no effect on the individual's probability of survival. So what does that mean? Typically, these are some sort of natural climactic event, or even anthropogenic, which means by humans, right? So it could be pollution, habitat destruction, fire, floods, volcanoes, severe storms, weather, earthquakes, oftentimes things that we think of as abiotic, not living, that influence it, and kind of totally random, right? Not just because there are a lot of individuals in one given space. Will we see density independent factors really affect our population size? So I like this graph. It kind of helps me understand things. Density-dependent factors really depend on the population size, right? The higher the population, the stronger the effect, right? So as population grows, all of a sudden it will decrease. Density-independent does not depend on the population size. The effect is always the same no matter what the density of that specific population is. And lastly, I want us to think about population size as really depending on resources, right? And we saw this before, our carrying capacity K. When food is available to a population, right, we're going to see that population kind of thrive. We're going to see size increase, right? More food, more offspring, survival rates are going to increase. And so we might actually see a little bit of an overshoot of our carrying capacity, our average, if you will, in our population size. But as it becomes, those resources start to limit again, right, we're going to see that population decrease. When food starts to become less available, we'll see population size decrease, reproduction rates decrease, and offspring survivability decrease as well, because there's just not as much there. As it starts to change, you could see that population size increase and decrease and go back and forth, right? So when we talk about carrying capacity, we're going to talk about a number, right? But just know that the population isn't always exactly that number because of those density dependent factors. And then even sometimes those density independent factors that could come in and influence a population sort of unexpectedly. So I hope that helps us understand how population sizes change and get affected, and I hope you have a great day.